In 1971, Hawking showed under general conditions that the total area of the event horizons of any collection of classical black holes can never decrease, even if they collide and merge. This result, now known as the second law of black hole mechanics, is remarkably similar to the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease. As with classical objects at absolute zero temperature, it was assumed that black holes had zero entropy. If this were the case, the second law of thermodynamics would be violated by entropy-laden matter entering a black hole, resulting in a decrease in the total entropy of the universe. Therefore, Finkelstein proposed that a black hole should have an entropy, and that it should be proportional to its horizon area. The link with the laws of thermodynamics was further strengthened by Hawking's discovery in 1974 that quantum field theory predicts that a black hole radiates blackbody radiation at a constant temperature. This seemingly causes a violation of the second law of black hole mechanics, since the radiation will carry away energy from the black hole, causing it to shrink. The radiation, however, also carries away entropy, and it can be proven under general assumptions that the sum of the entropy of the matter surrounding a black hole in 1/4 of the area of the horizon as measured in Planck units is, in fact, always increasing. This allows the formulation of the first law of black hole mechanics as an analog of the first law of thermodynamics, with the mass acting as energy, the surface gravity as temperature, and the area as entropy. One puzzling feature is that the entropy of a black hole scales with its area rather than with its volume. Since entropy is normally an extensive quantity that scales linearly with the volume of the system, this odd property led Gerard T. Hooft and Leonard Susskind to propose the holographic principle, which suggests that anything that happens in a volume of spacetime can be described by data on the boundary of that volume. Although general relativity can be used to perform a semi-classical calculation of black hole entropy, this situation is theoretically unsatisfying. In statistical mechanics, entropy is understood as counting the number of microscopic configurations of a system that have the same macroscopic qualities, such as mass, charge, pressure, etc. Without a satisfactory theory of quantum gravity, one cannot perform such a computation for black holes. Some progress has been made in various approaches to quantum gravity. In 1995, Andrew Strominger and Qumran Vafa showed that counting the microstates of a specific supersymmetric black hole in string theory reproduced the Finkelstein-Hawking entropy. Since then, similar results have been reported for different black holes both in string theory and in other approaches to quantum gravity like loop quantum gravity. Another promising approach is constituted by treating gravity as an effective field theory. One first computes the quantum gravitational corrections to the radius of the event horizon of the black hole, then integrates over it to find the quantum gravitational corrections to the entropy as given by the Wald formula. The method was applied for Schwarzschild black holes by Calmette and Kuipers, then successfully generalized for charged black holes by Campos Delgado.